One note before the recording starts, there was an error during the class when talking about the Nernst equation. E equals E naught minus RT over NF times the ln of Q. If you do this at 25 degrees C and plug in the values for R and F, you get the equation on the bottom of the screen. E equals E naught minus 0.05916 over N times log of Q. During class, I got confused and I switched the bottom to LNQ, and I shouldn't have. So I have corrected that in the slides that are now posted, but in the video itself, I'm using LNQ. It should be log Q. Okay, so the equation at the bottom is the one you should use for the Nernst equation when figuring out the potential.
A few of you need to see me after class. If your name's up there, come by and see me after class. All right, so what do we have going on? We have basically 3 weeks left. Okay, we have this week, next week, which has Thanksgiving, but Thanksgiving's on Thursday, Friday. So that means we have a normal week of class next week. And then one more week, and then finals. Okay, so 6 more lectures. Homework is due on Sunday. A reminder about grades. Your homework grade is 175. Attendance caps out at 50. So if you're already at 50, you're good. You should still keep on coming, but it doesn't go above 50. All right. So last time, also I'll put something on there next time. SOTIs are open, so make sure you can do SOTIs for all your classes. All right. Last time we talked about electrochemistry, and we talked about electrochemical cells. Right? In electrochemical cells, we have 2 electrodes. At those 2 electrodes, we have redox occurring. At one, reduction occurs. At the other, oxidation occurs. And we have electrons going from one side to the other. The electrode where we have a gain, I don't have it on this slide. The electrode that has oxidation, we call that the anode. The electrode where we have reduction is called the cathode, okay? And the anode becomes negative because it's producing electrons. The cathode is positive, right? Because it requires electrons. And so electrons flow from the anode to the cathode. The main thing, the thing that has to work for us to get that electron flow is we need to close the circuit. And that's done via salt bridge. Okay? So the salt bridge allows for ions to go, in this case, they'll go opposite of the electrons. So chlorine will go this way, and potassium, which is positive, will go this way. And that electricity, those electrons, produce what's called electric potential. Okay? The electric potential is measured in volts. And so we did a calculation like this last time where we were told that we have this reaction and we could figure out the charge, right? And the coulombs produced. Okay? All right, the cell potential, okay, like I said, is in volts, and it's dependent on the chemicals involved and their concentrations. So this is a galvanic or voltaic cell, right? Notice we have zinc and zinc 2+ here, copper 2+ and copper here, right? We have both those. Now, we can write this as line notation. In line notation, we say what's happening at the anode first. So zinc is becoming zinc 2+, and then the salt bridge represented by the 2 lines, and then copper 2+ going to copper, that's the cathode. Okay. What happens if we have something, right? So here, the electrodes would be made of zinc and copper. Okay. What happens? Copper and zinc, those are good transmitters of electricity? What if there's something that's not? Then we can have an electrode in there, an inert electrode that basically takes the place of one of those. So in this case, we have magnesium, and magnesium 2 plus, that's our anode. And here we have H plus going to H2 at the cathode. But H2 gas, you can't make an electrode out of because it's gas. So what do we have there? We have platinum, and we signify that by having a third line. Questions? We finished up talking about the standard hydrogen electrode, or SHE, or SHE, right? It is basically H2 going to H plus, and we can use that as a standard electrode, and that we kind of define as 0. And we can put anything next to SHE, and we can say, okay, how much electricity do we get, right? What's the electric potential? So for instance, if SHE is our anode, and F2 goes to F minus, right, at our cathode, our cell potential would be 2.89. Right? If it were lithium plus going to lithium, it would be negative 3.04. This is what's called the standard reduction potential. We say standard by having that not up there. E not means standard conditions. Standard conditions meaning 1 molar for aqueous solutions, 1 bar for gases. The higher the electrode potential or the standard reduction potential, the more likely it is to get reduced. Okay? So what happens if I just kind of shrunk this? Let's say I have a cell containing copper 2 plus going to copper 2 plus slash copper and cadmium 2 plus in cadmium. So one of those will be my anode, one will be my cathode. I need to figure out which. Okay. So what do we do? Well, both of them can't be reduced. And by the way, we're going to use the dot cam today. I'll use the dot cam on, I guess, this. What is this? This is the left projector. Nope. We'll do it on the right projector. Switch. Okay. Is that better, or you guys think the opposite way? I think kind of everyone's kind of position here. Okay, so in this case, we have copper 2 plus and copper. We have cadmium 2 plus and cadmium. Let's see, let's zoom out. By the way, you won't see this on the video, but I'll post it on the page afterwards. Okay, so this is slide number 11. Okay, so they both can't be reduced. Why? If we have a transaction, right, and I'm going to gain money, that means you have to lose money, right? We can't both gain money, right? We're not, let's not, yeah, that would mean someone else would give us money, right? If it's just me and you, if I gain money, you have to lose money, right? Or if I lose money, you gain, right? So I need to figure out which one of these is going to be reduced. All right, I look up at my values and I see that E naught for copper is 0.339 volts, and for cadmium is negative 0.402 volts. Which one of those is going to be reduced? The copper or the cadmium? Why? It has a higher reduction potential, right? The one of us with the highest potential to become a basketball player is going to play in the NBA. I don't think any of us are, but it'd be the most likely, right? You have the highest potential, that means you're the most likely to be, in this case, reduced. So that means copper would be reduced, right? And this is reduction. We're going from 2 plus to 0. And what does that mean the cadmium has to do? It has to do the opposite, which is oxidation, right? So it's going to be the opposite. So we can calculate the cell potential, right? Which we'll put standard because we're under standard conditions. It is the difference between the two reduction potentials. Okay? So E cell is going to be the reduction potential of the anode minus of the cathode. So we said that's oxidation. This is, or sorry, that's. Sorry, give me 1 second. This is reduction, so that's the cathode. This is the, and therefore it's of the cathode, sorry, minus the N. And so I can do this by saying that E cell equals 0.339 volts minus negative 0.402 volts. And that will end up giving me 0.741 volts. Notice it is positive. Because it is positive, that means that this will happen spontaneously. Okay, this would be a galvanic cell, right? The opposite would be one where it would be negative, in which case it's not spontaneous and we have to put electricity into it. All right, now let's just look at the overall reaction. If I have copper 2 plus going to copper and cadmium going to cadmium 2 plus, one of the key things is that when we talk about the entire reaction, it has to include the same amount of electrons. Okay, so copper 2 plus going to copper. Are we gaining or losing electrons? How do we tell? It's math. It's easy, right? How do we go from 2 plus to 0? Right? I can either add electrons to this side, but if I add electrons to this side is going to become more negative, right? I want them to be the same, so I have to add electrons to the side that's higher. So it's gaining 2 electrons. So 2 negative plus 2 positive equals 0, and this side is 0 too. So what happens on my cadmium? In that case, it's losing electrons, and in that case, it's losing 2 electrons. So in this case, well, it's fairly easy because both of them involve 2 electrons. So the 2 electrons cancel out, and I get that copper 2 plus copper, or sorry, plus cadmium goes to copper plus cadmium 2 plus. That is my overall reaction. Yes? You never subtract reaction. We've seen a lot of chemical reactions now. We never have negative, right? It's never H2O minus HCl goes to form. Yeah. So whenever, if we want to do negative, that means it's on the other side. Okay. So if I wanted to put copper cadmium minus, I would just put it on the other side. Okay. All right. Now, notice how I messed up the cathode and anode. I'm like, oh my goodness, right? The key thing is that it's always going to give you something positive if it's thing. So you can kind of just take the difference and do the absolute value if you want. All right. Now, what we just looked at was under standard conditions. Standard conditions being 1 molar or 1 bar if we're talking about gases. If we're not under standard conditions, then we're going to have non-standard reduction potentials, which we just show by not having that naught up there, right? So the E naught up there means it's standard conditions. If it's not standard, it will not have that naught. Okay. And so this is any other conditions. Here's a question. In the real world, are we usually at standard conditions? No. Standard conditions, E naught applies to a very slim thing, right? If it's exactly 1 molar, right? But in reality, things are going to be different, right? Even if you had, let's say, a battery or a reaction, and you started off with 1 molar, well, after a little time, it'll no longer be 1 molar, right? We know this because we've dealt with batteries enough, right? My cell phone, right? It used to charge all the way up. Now it charges like halfway up or a third of the way up, right? Because things decay with time. Okay, so. And 1 molar is very concentrated, right? In our body, if I had 1 molar Na plus, I would die, right? It's very concentrated. So usually what we do is we have to use something called the Nernst equation. So the Nernst equation says that E, the standard reduction potential, or sorry, the reduction potential is equal to E naught, the standard reduction potential, minus RT, where R and T are constants. R is the ideal gas law constant. Okay. T is temperature in Kelvin. N is the number of electrons involved in the redox reaction. So negative RT over NF times log of Q. And remember Q is from our equilibrium constant. Or our reaction quotient. If we're at 25 degrees Celsius, so I plug in 298.15, we get that E equals E naught minus 0.05916 over N. So I plugged in for R and F, which are constants. I plugged in this for temperature times log of Q. That's the one we'll be using most. All right, so remember that, for A going to B involving N electrons, right? Our Q is the concentration of B raised to its coefficient over the concentration of A rose to its coefficient, and N would be the number of electrons involved. All right, so let's look at the reduction potential for Au3 plus 2 electrons going to Au plus. If we have 0.467 molar Au3 plus and 0.038 molar Au plus. We can look up E naught in Appendix C of the book. Always be careful when you look these up that notice both these involve gold. But the specific reduction potential we want is the one that involves gold at the specific charges we're looking at. So in this case, we're going from 3 plus to plus. So that means we'll use 1.41. Okay. All right. So I'm going to let you guys do this for a little bit. So we know what E naught is. N is the number of electrons, and then calculate Q and plug that in there, and let's see what we get. Where's the is which we give me 1 second. Oh shoot! Sorry. Yes, it is ln of q. Sorry. All right. Let me just. I have it on other slides. I don't know why it was on this one. All right. Okay, so sorry about that. The Nernst equation E equals E naught negative 0.05916 over n ln of q. Okay, I'll fix that one above. All right, so let's do this equation together, or this calculation together. So first, we're going from AU 3 plus to AU plus. So that involves 2 electrons. So n equals 2. We know what E naught is. It is 1.41 volts. We got that from the chart on the previous slide. And that Q, well, we're going from AU3 plus to AU plus, so it's going to be the concentration of AU plus over the concentration of AU3 plus. Right? It's 1-to-1, so we don't include that, so we can plug these in. We plug that into our calculator. We get 0.08137. So we plug that in. So 1.41 minus 0.05916 over 2 times the ln of 0.8137. All right, let's just pull. Okay, so that's negative 0.20616. Okay, be very careful to include the negative in this case, right? And so that will become 1.41 plus 0.00609821, right? And so when we add these up, we get 1.416 or 1.42 volts. So our cell potential has, or our reduction potential has shifted from 1.41 to 1.42 because we're not at 1-to-1. Questions? Let me ask a question, right? What happens if I take that equation at the top and I was under standard conditions? Okay, if I was under standard conditions, that means that what are my concentrations? 1. Okay, so in this case, if I have concentrations of 1, my Q would be 1/1 or 1. Okay, and the ln of 0, or sorry, the ln of 1 is 0. Okay, so I'd have E0 minus 0. So then if I'm under standard conditions, I get that my E equals E0, which makes sense. Okay, so that's why it works out. Okay, so we have that. Switch this over. Under standard conditions, we have that the E of the cell is the cathode minus the anode. The same holds true for under non-standard conditions, except we need to calculate those non-standard conditions. So let's do an example. So let's say we have a cell with two half cells. The first is a silver electrode coated with silver chloride in a 0.5 molar KCl solution. Okay. The second is cadmium electrode in 0.01 molar cadmium nitrate. We want to first write the net cell reaction, the line notation, and finally calculate the voltage. All right. So what's going on here? Okay, so our cell consists of two things. The first is silver and silver chloride. The second is cadmium and cadmium nitrate. All right, if I look at from Appendix C, I can see that, okay, there is AgCl plus one electron going to form Ag solid plus Cl minus. Okay, this one's a little bit different than some of the other reduction potentials we see. Okay, notice it's written in this way. Because what's the oxidation number for the silver in silver chloride? What? 1 plus. Why? Because the chlorine is 1 minus, right? So it's going from 1 plus to 0, right? Our cadmium, what's the charge of our cadmium here? What? 2 plus. Why? Because nitrate is minus. So that means I have cadmium 2 plus 2 electrons going to form cadmium. Okay, notice if I look at the table here, I have 2 values for my silver chloride. I have 2 values. One, it just says as 0.22. The other, it says as 0.197 under saturated KCl conditions. Okay. Are we at saturated KCl? We don't know, right? But it probably not because it doesn't say saturated KCl. So we may have to check that out. All right. Now, we'll come back to this, but why does it say saturated KCl, right? Well, it's because a lot of times you use electrodes that happen to have saturated KCl. You guys all did this when you used the pH meters. The pH meters had KCl inside them, right? That little probe you used had KCl in there, okay? All right, but we'll come back to that. All right, so for this, we have that it is 0.222. That's its standard reduction potential. And for cadmium, it's negative 0.402. So which one of these is going to be reduced? AgCl. Why? It has the higher value, it has the higher potential. Okay. So having the higher potential means you're more likely to be reduced. All right, so that means this one will be reduced. That means that it can stay as is. But what has to happen to our cadmium reaction here? It can't be reduced. We can't have both of these as is. So what do we have to do to the cadmium reaction? We reverse it, right? So if it can't be oxidized, or sorry, if it can't be reduced, that means it will be oxidized. Does that look good? If I were to add these up, shaking the hands because we have to multiply this by 2. So we'd have 2 AgCl plus 2 electrons going to form Ag solid plus Cl, sorry, 2 Ag solid plus 2 Cl minus. We're not changing the cadmium reaction. And then when I add these two up, these two go away. I get 2 AgCl. That's cadmium solid. All right, so this is our net reaction, okay? So the AgCl is becoming Ag, that's happening at the anode, whereas the cadmium is becoming cadmium 2+, that's happening at the cathode. So now we want to write a line notation. So to do it in line notation, what comes first, anode or cathode? Anode, right? It's easy when things are in alphabetical order, right? When things are against alphabetical order, it's tougher, right? But it's always anode first, then cathode. So I can write that I have anode will be oxidation, cathode will be reduction, right? So that means that this is our anode. So that means cadmium 2+, and then AgCl solid, Cl solid here as well. Notice I put the Ag solid at the end. Why? There are 3 things involved in this: AgCl, Cl minus, and Ag. Why do I put the silver at the end? Because the first one and the last one, the outside, those represent the actual electrodes, right? The metal you put into the water, okay, or in the aqueous solute. So I have an electrode made out of cadmium solid, and I have an electrode made out of silver solid. And if you look at up there, what does it say? A silver electrode and a cadmium electrode, right? So that's why I put those at the end. Okay. All right. Now there's one thing wrong. There's one thing I haven't written down. Okay. As written, this looks like it is under standard conditions. Okay. If I don't write down what the concentration is, we assume it's 1 molar. This is not under standard conditions. I know because I say it's 0.5 molar KCl and it's 0.01 molar cadmium. So I need to include those into my line notation. Yes. It was in the problem itself, right? The initial one, and I'll put it back on this one. I was told that it had those, right? If I wasn't told what the concentrations is, I have to assume it'd be 1 molar. But in this case, I'm told what it is. Why don't I have concentration for the solids? Because concentrations can't have, or solids can't have concentrations, they're just solids. And notice here, I don't include, or I don't have to include the cadmium, the nitrate, right? Because nitrate's just there. Question. All right, the third thing that's asked of us is to calculate the voltage. Okay, so let's just calculate a voltage, right? Well, could I just take the 0.222 minus the negative 0.402? I would get 0.624 volts. That would be easy, but that's not what we want. What is this number? The standard, right? Calculating standard conditions is really easy because you just look at a table, you find those two, you figure out which one's getting oxidized, which one's getting reduced, right? And you calculate the difference, right? Under non-standard conditions, now we have to use the Nernst equation, okay? So let's do that. All right, so we have at our anode, we have cadmium going to cadmium 2+, right? And we're told that its E naught is equal to negative 0.402. And at the cathode, we have AgCl going to form Ag plus Cl minus. And this we have at 0.222 volts. Okay. All right, so let's go ahead and calculate these. All right, now one thing is, remember we had 2 electrons here, and here we had to double it. So it's 2 AgCl plus 2 electrons going to 2 Ag plus 2 Cl minus. So in order to calculate these, I'm going to start with the E for the anode, right? By the way, a lot of times we just call this E minus, signifying the anode. So that's going to be E naught minus 0.05916 over N times ln of Q. That's negative 0.402 volts minus 0.05916 over 2 times ln of Q. Yes. Sorry, what was that? Because I'm doing it for the anode. We're going to do it for the anode and the cathode, right? So I'm going to do this for the anode, then you guys are going to do it for the cathode. Okay, so what is our Q in this case? Our Q for this equation is just cadmium 2 plus, right? Not squared. Nothing. And notice we don't have cadmium because cadmium is a solid. So that's just going to be 0.01 All right. I take that back. Right. Okay, so this is the E naught, right? Actually, for the other reaction, cadmium 2 plus going to cadmium, right? Plus 2 electrons. So in this case, our Q isn't going to be just the cadmium 2 plus. Our Q is actually 1 over the cadmium 2 plus. That'll be 1 over 0.01. So that'll be 100. So I plug in ln of 100 into there. This ends up giving me negative 0.402 volts minus 0.02958 times the ln of 100. Which is 4.605. That's negative 0.402 volts minus 0.136. And so that will be negative 0.538 volts. That is the standard reduction potential at the anode. Let's do the same thing for the cathode. Okay, so there's my reaction occurring at the cathode. I have 2 AgCl plus 2 electrons going to form 2 Ag plus 2 Cl minus. Okay. So I want to figure out what our values are. So I have 0.222 volts. Minus 0.05916 over 2 times ln of Q. what is our Q? For that equation right there. It helps if we have charges or our states. So for that cathode, what's our Q can be? 0.05 squared. So notice it's just our Cl minus, our concentration of Cl minus squared. Okay. These are solids, so they're not in there. So our Q equals Cl minus squared. Okay. So I can plug in my Cl minus, which is over there. I have that it's 0.5 molar. So that's going to give me 0.25. This E plus is equal to 0.222 volts minus 0.02958 times the ln of 0.25. Which is 1.38. Six or negative. Be very careful about the negative sign here. Oops. The negative sign here and the negative sign here cancel out, so that's a positive, right? And so that gets me 0.263 volts. So now we've calculated E positive, we calculated E negative. So to figure out the entire cell potential, it's the difference between the two. And 0.801. Yes. All right. Questions? So when we're under non-standard conditions, we need to go through and we need to make sure that we correct for the actual concentrations. All right, I'll let you guys write that down. Let me just look one thing up. Yes. Yeah. Before you vote, right? So in this case, right up here, we use the one, this one, because this relates to this right here. Okay, so that's why we have to do the one before we rotate it. Yeah. Give me 1 second. All right. Any other questions? Okay, so the Nernst equation tells us that the cell potential of electrodes depends on their concentrations. Now, as reactions occur, the concentrations will change. And that means that as the reaction occurs, the cell potential itself can also change. Okay, so what we just calculated, right, in this example was at the very beginning of the reaction. Okay, but as the concentration of Cl minus changes and as the concentration of cadmium changes, the cell potential will change. Okay. One way to do this, or one way to get around this, right? So that's very annoying, right? If I set up a cell reaction, and the cell potential keeps on changing, that's annoying. So one way to get around this is to keep the concentrations constant. Okay? And if we keep the concentrations constant, we'll have a constant cell potential. Okay? We do this often with what is called a reference electrode. A reference electrode is one that maintains a fixed potential. And it does this by having constant concentration. Reference electrodes are often used as indicator electrodes, right? Because we can use these to calculate an analyte concentration. All right, so an example of a reference electrode is what's called a silver chloride reference electrode. That's the one we just were talking about. Okay. A silver chloride reference electrode has Ag, silver electrode, with a solid KCl. And because you have solid KCl, what that means is the chloride concentration is saturated. It's concentrate. It's constant. This is shown as this, right? Ag, AgCl, Cl minus, right? And it has a cell potential of 0.197 at 25 degrees Celsius. What we can do is we can take this and put it into an electrode, right? One single electrode that will have your silver and your silver chloride, right, inside of that one electrode. Here's an example, right? So what you have is you have a container. It has a porous plug that allows only ions to get through. You have solid KCl. And then you have your silver electrode. And so what happens is the chloride concentration inside that electrode stays constant. Okay. This is what you used as a pH meter in one of your classes. Another example is what is called the Calomel reference electrode. The Calomel reference electrode uses Hg2Cl2, so mercury chloride, it's liquid mercury and Cl minus. Right? So here's an example of this, right? So you have liquid mercury in there, and then you have Hg2Cl2 there. You did not use a Calomel reference electrode, okay? Why do you think we wouldn't want to use this type of electrode that often in lab? What do you know about Hg? What is Hg? Mercury. What do you guys know about mercury? It's dangerous, right? Mercury is toxic. Mercury is pretty cool. You've seen it? It's like that silver, right? Silver looking, right? But it's dangerous, right? So that's why we typically wouldn't use mercury, this electrode, unless it's the only one you could use. Okay. All right. All right, so let's do this problem. Let's say we want to calculate the voltage for a cell consisting of iron 2 plus, iron 3 plus, with 0.2 molar Fe2 plus and 0.02 molar Fe3 plus, and a saturated silver chloride electrode. Okay, so this is our silver chloride electrode. Usually it's not like this. Usually it's just a probe. And on the other side, we have Fe3 plus going to Fe2 plus. So let's use this information to figure out the voltage associated with this. All right. All right. So we need to find E plus and E minus. So for the iron, we can use the Nernst equation. But because we're using a standard electrode, that standard electrode is going to have a constant cell potential of 0.197. This is going to be constant. Why? Because it's always 0.197 because it's concentrated or it's saturated. But now we need to figure it out for the iron. All right, looking at the back of the book, we can find standard reduction potentials for this reaction of 0.771, 0.732, 0.767, 0.746, and 0.68, right? These are, if I had 1 molar formal charge of HCl, 1 molar of HClO4, nitric acid, and sulfuric acid, okay? Which one of these pertains to this case? Do we have HCl? Do we have HClO4? Do we have nitric acid? Do we have sulfuric acid? No. So we just use the standard value they have, the one that doesn't have any preconditions, right? So in this case, it's 0.771. That's what we're going to use as our E naught. I'm going to give you guys a couple minutes to try to calculate the reduction potential for this case. Who hasn't signed? All right, so if I go back to the previous slide, I have that 0.771. That is our reduction potential, okay? So if I have Fe2 plus and Fe3 plus, which one of these corresponds which one of these is reduction? Fe2 plus going to Fe3 plus or Fe3 plus going to Fe2 plus? Three plus to 2 plus, right? So this 0.771 corresponds to Fe3 plus going to Fe2 plus by gaining 1 electron, right? And you could actually go back, and if you have the table, you can see Fe3 plus 1 electron goes to Fe2. Okay, so that's our reaction occurring here. So that means N equals 1. And in this case, our Q would be Fe2 plus over Fe3 plus. Okay. So let's look at our problem. Our Fe2 plus is 0.2 molar. Our Fe3 plus is 0.02 molar. So that's going to give us 10. So we have ln of 10. That'll be 2.3. Sorry, let me. Legible. 2.3 times 0.0596. Zero point 634 volts. Now, a key thing is that is for my iron. My overall goal is to find it for the entire thing. Yes. Oh, wait, where? Oh, 5916. Oh, shoot. Yeah. Thank you. I don't think that's going to make a huge difference, but let's just see. So 2.3 times 0.05916, that'll be minus 0.136, right? And so that's going to give me 0.635. Thank you very much. Okay, so that's for one electrode. Our other electrode is 0.197 volts. Okay, so which one is gonna have reduction occurring? The iron or the silver? What? The iron, because it's higher. It has a higher reduction potential. Okay, so that means that this is my reduction. This will be my minus, right? My oxidation. So it's 0.635 minus 0.197. And I get 0.438 volts. All right, any questions? All right, so that is it for electrode potentials. Okay. Next time, we're going to talk a little bit more about redox reactions. But here's your list of terms. These are the calculations you need to know for this section. I will post the study problems next lecture. And then next time, we're going to talk more about electrode measurements, right? Including the electrodes you actually used in the lab, okay? And then we'll talk about some titrations. All right, questions? All right, I'll see some of you in 15 minutes, other of you on Wednesday. If you didn't sign, you didn't. Thank you. It was perfect. And Diane, Catherine, is Eduardo here? I don't think so. Second.